To understand why scientists pay such close attention to Earth's magnetic field, you first need to picture it as a massive invisible shield that surrounds our planet. This shield, known as the magnetosphere, is constantly at work fending off dangerous particles streaming from the sun and high-energy cosmic rays that arrive from beyond our solar system. Without it, the relentless solar wind would slowly strip away our atmosphere, a process that may explain why Mars lost its once thick blanket of air and became the barren world we see today. For centuries, humans had no way of knowing how strong or stable this shield really was. But starting in the early 19th century, researchers began to make careful measurements of the field's strength and position. These observations, combined with modern satellite data, reveal something surprising. Earth's magnetic field has been steadily weakening. According to measurements from the European Space Agency's SWARM mission, the field has lost roughly 9% of its overall strength during the last 200 years. This decline is not uniform across the globe. One of the most striking features is an enormous zone of weakness stretching from South America to Southern Africa. Scientists call it the South Atlantic Anomaly, and within this region, the field is about 1/3 weaker than the global average. It is not just a scientific curiosity, it creates real problems for technology. Satellites passing through the anomaly experience surges of radiation that can interfere with electronics, damage sensors, and shorten their operational lifespans. Astronauts who travel through the area report flashes of light caused by cosmic rays striking their eyes, a reminder of how exposed spacecraft are when the magnetic shield thins. Even more unsettling, the anomaly is changing over time. It has been expanding, and new data suggests it is splitting into two separate weak spots. One of these is drifting westward at roughly 20 kilometers per year, a pace fast enough to matter for satellite operators who must plan years in advance. This instability does not prove that a magnetic flip is imminent, but it shows how dynamic and unpredictable the system can be. At the same time, the magnetic North Pole has been wandering in unexpected ways. First recorded in the year 1831, it has traveled more than 1,000 kilometers from its original position in the Canadian Arctic. During the late 20th century, it began moving with unusual speed, at one point covering about 55 kilometers per year on its path towards Siberia. The pace has since slowed, but the shift was so significant that navigation models used in everything from smartphone maps to aviation systems required unscheduled updates to remain accurate. A field that is weakening, a growing anomaly in the South Atlantic, and poles that refuse to stay put. It is no wonder these trends spark headlines about a possible magnetic apocalypse. But before we can judge how serious the situation is, we need to understand what actually powers this field and why it sometimes behaves so chaotically. For that, we must travel deep below our feet to the restless core of the planet. Deep below the Earth's crust, nearly 3,000 kilometers down, lies the outer core. It is a vast ocean of molten iron and nickel, hotter than the surface of the sun in some regions, swirling in constant motion. These liquid metals move because of heat escaping from the planet's interior, creating enormous convection currents. As they churn, they generate powerful electric currents, and those currents produce the magnetic field that wraps around our planet. This invisible engine is called the geodynamo, and it has been running for billions of years. The geodynamo is not a perfectly steady machine. It is chaotic and unpredictable. Slight changes in the flow of molten metal can ripple outward, altering the field's strength and even its orientation. In Earth's distant past, these shifts sometimes became extreme enough to flip the entire field, swapping north and south. We know this because lava flows that cooled millions of years ago locked in magnetic minerals, preserving a record of ancient pole positions. By studying these frozen compasses, geologists have confirmed that full magnetic reversals have occurred hundreds of times in Earth's history. The last major reversal happened about 780,000 years ago, and the process likely took thousands of years to complete. During that time, the field did not simply switch off. It grew weaker, broke into chaotic patches, and then slowly reorganized itself with opposite polarity. For most of Earth's history, this cycle has been survivable. Life persisted through countless flips, suggesting that the planet can endure the process. But here's the catch. Humanity has never lived through one. All of our power grids, communication satellites, and navigation systems are designed for a stable magnetic shield. A reversal in the modern era would not just be a scientific curiosity, it would be a global hazard. Now imagine this scenario as reality. The molten engine below our feet begins to shift in unexpected ways. The field weakens further, shrinking to a fraction of its former strength, while chaotic regions of magnetism erupt across the globe. In some places, compass needles spin uselessly, pointing in no consistent direction. The South Atlantic anomaly grows larger, exposing satellites to ever greater radiation damage. Navigation systems misfire, high-altitude flights face rising radiation risks, and the skies above Earth become a dangerous place for both astronauts and aircraft. In this hypothetical, humanity would be watching the early stages of geomagnetic reversal unfold in real time. It would not happen overnight, but the creeping instability would be enough to shake global confidence. Scientists monitoring the geodynamo deep inside the planet might warn that we are entering a transition phase unlike anything our species has ever experienced. The question would no longer be whether a reversal is possible, but how long it would take and how disruptive it might become. As Earth's magnetic field falters, the consequences begin to surface in everyday life. Normally, this shield deflects most of the charged particles streaming from the sun, but in this hypothetical scenario, as the field weakens, those particles punch deeper into the atmosphere. Auroras, usually seen only near the poles, would blaze across skies in places that have never witnessed them before. Cities in regions like Southern Europe, North America, and even parts of Africa might suddenly glow with shimmering curtains of light. It would look breathtaking, but it would be a warning. With more radiation slipping through, the skies above Earth grow hostile. Commercial airlines flying high-altitude polar routes would be exposed to dangerous levels of cosmic rays. Crews and passengers could face higher health risks, forcing airlines to ground or reroute flights. Satellites orbiting above would not fare much better. Without a strong shield, their electronics would be battered by charged particles, leading to malfunctions, power losses, or complete shutdowns. GPS navigation systems could flicker on and off, leaving both pilots and everyday drivers without reliable signals. On the ground, people might not notice the invisible storm at first, but its effects would creep into daily life. Power grids, especially in high-latitude regions, would become vulnerable. The currents induced by solar activity could surge through electrical systems, frying transformers and plunging cities into blackouts. Communication networks would falter, making it difficult to send messages or access information during critical moments. Farmers relying on satellites to monitor crops would lose data, and shipping companies that depend on precise navigation would be left adrift. In this imagined world, humanity would be forced to adapt to skies that no longer protect us. The once reliable magnetic shield would become patchy, exposing billions of people to vulnerabilities they had never considered. Governments might begin issuing radiation warnings alongside daily weather forecasts. Space agencies could scramble to shield astronauts aboard stations, while engineers race to design satellite systems capable of surviving the harsher conditions. The changes would not arrive all at once, but with each passing year, the cracks in our shield would widen. This is the stage where the reversal stops being a scientific curiosity and becomes a global emergency. The question would shift from "is this happening?" to "how can we survive the decades of instability ahead?" With the magnetic field weakened and chaotic, the strain on modern technology would escalate dramatically. Satellite-based communications, including the internet, television broadcasts, and global phone networks, would experience frequent disruptions. Weather monitoring satellites would struggle to track storms accurately, leaving populations vulnerable to hurricanes, tornadoes, and other extreme events. Financial systems that rely on satellite timing signals could face interruptions, affecting transactions across the globe. Power grids would bear the brunt of this unseen storm. Solar flares, normally deflected by a robust magnetosphere, would induce massive electrical currents in transmission lines. Transformers could overload and explode, triggering cascading blackouts across entire regions. Cities could be plunged into darkness for days or even weeks, while engineers scrambled to replace damaged equipment. In remote or vulnerable areas, recovery might take months, leaving millions without heat, refrigeration, or clean water. Transportation systems would falter as well. GPS signals, already compromised by satellite malfunctions, would become unreliable for shipping, aviation, and road networks. Cargo planes and ships might be forced to navigate by older, slower methods, slowing the global flow of goods. Emergency services would struggle to coordinate during crises, increasing the risk of accidents and delayed responses to disasters. Even scientific research and space exploration would face setbacks. Space telescopes and probes, previously shielded by the magnetic field, could experience instrument failures or shorten lifespans. Astronauts aboard stations or traveling beyond low Earth orbit would be exposed to higher radiation doses, potentially forcing mission cancellations. The ripple effects would be felt across industries, from agriculture and healthcare to communication and defense. In this imagined scenario, the magnetic field flip transforms from a geological curiosity into a challenge that touches every corner of human society. It would not be instantaneous, but over decades, the combined stress on infrastructure, technology, and logistics would create a world in which adaptation becomes essential. Humanity would be forced to innovate rapidly to maintain the systems we rely on daily, or risk being severely hampered by forces billions of years in the making. As the magnetic poles shift and the field becomes chaotic, the impact on Earth's wildlife would be subtle but significant. Many species rely on geomagnetic cues to navigate. Migratory birds, sea turtles, salmon, and even certain insects. During a prolonged multipolar phase, these internal compasses would become unreliable, causing confusion during seasonal migrations. Sea turtles, for instance, could struggle to find nesting beaches, while birds might overshoot or undershoot traditional breeding grounds. Marine life could also face challenges. Some fish use the Earth's magnetic field to orient themselves in the oceans. A jumbled field might alter their migration patterns, affecting feeding cycles and predator-prey interactions. Over time, these disruptions could ripple through entire ecosystems, forcing animals to adapt using alternative senses like the sun, stars, smell, or ocean currents. Plants, while not directly influenced by magnetism, could feel indirect effects. Altered animal behaviors could change pollination patterns, seed dispersal, and predator dynamics. Some species might thrive in new niches, while others could decline. Over centuries, this period of geomagnetic instability could drive evolution in unexpected ways, creating new adaptations and species interactions. Humans would witness strange phenomena as well. Birds might land in unusual locations, bees could fail to return to hives, and migratory mammals could appear in areas far from their normal ranges. Scientists studying these disruptions would gain invaluable insight into how sensitive life is to geomagnetic forces. But for the average person, the changes would mostly be curious or inconvenient, rather than catastrophic. In this hypothetical scenario, the natural world continues to operate, but under a stress test unseen in modern history. Adaptation would be the key for all life forms, just as humans must adapt to technological and societal challenges caused by a fluctuating magnetic shield. The planet's resilience, built over billions of years, would ultimately keep ecosystems functioning, even amid chaos. With all the potential disruptions in mind, the next question is obvious. Is a geomagnetic reversal imminent? Scientists are constantly monitoring the Earth's magnetic heartbeat using a network of satellites, observatories, and ground-based sensors. The European Space Agency's swarm satellites, launched in 2 phases starting in 2012, provide real-time measurements of the field's strength, direction, and anomalies. These observations allow researchers to track changes with unprecedented precision. Current data confirms the field continues to fluctuate, but these fluctuations are within the natural historical range. While the South Atlantic anomaly grows and shifts and the magnetic North Pole wanders, these are not clear signs of a full-scale reversal. In fact, geological records show that field strength often drops and recovers multiple times before any actual pole flip occurs. Scientists call these excursions, and they are temporary, sometimes lasting only a few hundred years. Despite the dramatic media headlines, there is no evidence that a complete flip will happen within the next several centuries. The geodynamo is a chaotic system impossible to predict precisely, but current trends do not indicate an imminent catastrophe. Instead, what we are witnessing is a rare opportunity to study the dynamics of our planet in real time, refining models that could one day predict long-term magnetic behavior more accurately. In the meantime, preparations focus on resilience rather than panic. Engineers are designing satellites to withstand higher radiation levels, power grids are being reinforced against solar storms, and navigation systems are being updated to accommodate a shifting magnetic landscape. By taking these steps now, humanity can reduce potential disruption if a prolonged multipolar phase eventually occurs. For everyday life, the message is clear. A magnetic field flip would be slow, gradual, and largely manageable. Life on Earth has endured many flips before, and our technology, while vulnerable, can be adapted. This is not an apocalyptic scenario, but a long-term challenge that encourages us to build systems capable of weathering the Earth's natural cycles. The key takeaway? Awareness, observation, and adaptation are our strongest defenses. By respecting the planet's forces and preparing intelligently, we can face a future magnetic flip with knowledge instead of fear, turning a potential disaster into an opportunity for scientific discovery and technological resilience. So what does all this mean for us as a civilization? A geomagnetic reversal is not an immediate apocalypse, but it is a slow-moving planetary event that could challenge the systems we rely on. Over thousands of years, the magnetic poles could wander unpredictably, satellites might experience more frequent radiation damage, and power grids could face unusual stress during solar storms. For scientists, engineers, and policymakers, this presents a multi-generational planning challenge. The good news is that life on Earth, from single-celled organisms to humans, has survived hundreds of past reversals. Our atmosphere remains a steadfast shield, and even a weakened magnetic field provides some protection against cosmic and solar radiation. Technology is the main vulnerability, but unlike early humans, we have the foresight and tools to adapt. By upgrading satellites, reinforcing grids, and developing radiation-hardened electronics, humanity can continue functioning even under a weakened or chaotic magnetic field. This scenario also serves as a reminder of the planet's dynamic nature. Earth is not static. It is constantly reshaping itself, from the molten core to the shifting crust above. Understanding the geodynamo and monitoring the magnetic field in real time allows us to anticipate long-term changes rather than react in panic. It highlights the importance of science in reducing uncertainty and preparing for natural phenomena that unfold over millennia. In essence, a magnetic field flip is less about instant catastrophe and more about resilience. It is a test of how well we can observe, innovate, and adapt to planetary forces that operate on scales far beyond a human lifetime. Awareness, preparation, and continued research are the keys to thriving in a world where the compass may no longer point where it used to. So while your compass might one day spin wildly, the Earth will still turn, the sun will still rise, and humanity will still endure. The magnetic poles may flip, but life goes on, and with knowledge and foresight, we can face these slow-motion changes without fear. This is the fascinating intersection of geology, physics, and human ingenuity. A reminder that even the planet's deepest secrets can be understood, and that science gives us the power to live safely in a world that is always in motion.